Hi everyone, welcome to the Fourier series class. In the last class, we have discussed about the f of x can be expanding as a Fourier series in the interval minus pi comma pi when f of x is a periodic function with the period 2 pi. In the last class, we have discussed about the expansion of f of x in the arbitrary interval minus L comma L with the length of the interval is 2L or with the period 2L. That is, we have discussed the Fourier series expansion of such functions. Such function f of x in minus L comma L is given by f of x is equals to a naught by 2 plus summation n is equals to 1 to infinity a n cos n pi x divided by L plus b n sin n pi x divided by L. The Fourier constants a naught, a n, b n are given by a naught is equals to 1 by L integral minus L to L or it is f of x dx, and a n is equals to 1 by L integral minus L to L f of x into cos n pi x divided by L dx. Bn is equals to 1 by L integral minus L to L f of x into sin n pi x divided by L dx. If the function is even, f of x is even in minus L comma L, we have f of x is equals to a naught by 2 plus summation n is equals to 1 to infinity a n cos n pi x divided by L. Suppose if the function is odd, only the sign terms we have summation n is equals to 1 to infinity bn sin n pi x divided by L we have discussed earlier. Now it's the time for expanding f of x in the interval. Yes, in the previous very first class we have taken the problems on minus pi comma pi. Later on we have discussed about the expanding f of x as a Fourier series when f of x is a even function and odd function in minus pi comma pi. Next we have discussed that is for restriction of the interval minus pi comma pi. If we choose the interval minus L comma L, we have expanded as a Fourier series in case of even and odd functions also. Suppose if the function is defined defined in the interval 0 comma L, right, or f of x is defined in 0 comma L, then how we are going to expand as a f of x as a Fourier series? That is, we are going to discuss today class about the expanding f of x as a half range Fourier series or half range cosine series and half range sine series. Half range expansions are Fourier cosine and sine series we have discussed. So far we have considered the Fourier series expansion of function which is periodic defined in the interval c to c plus 2L last class, right, length 2L. Now we consider the procedure to expand non-periodic function f of x defined in the half of the above interval. Here it is c to c plus 2L is given in the previous. Here I am going to consider the half of this interval, right? So now we consider the procedure to expand a non-periodic function f of x defined in the half of the above interval. Suppose if we take the function in minus pi comma pi, the half of the interval is what, 0 comma pi I am going to consider. If we take the function f of x in minus L comma L, the half of the interval is 0 comma L, right? Okay, in general I am writing, in general case I am writing here. Here it is defined in the half of the above interval is 0 comma L of length L. Such expansions are known as half-range expansions or half-range Fourier series. Right? Now, I am not considering the complete interval here. Half of the interval I am considering. That's why the series are called half-range Fourier series or half-range Fourier series expansions. Half-range expansion containing only cosine terms. In the expansion of f of x, in the half-range expansion of f of x, that is nothing but f of x which is defined in 0 comma L. In that expansion only cosine terms are having, that contains only cosine terms, we say that is half-range Fourier cosine series. In the similar way, if the Fourier series expansion of f of x in 0 comma L, the expansion contains only sine terms, we say that that is half range Fourier sine series, right, that contains only sine terms. Note that here it is, I am not considering the complete interval, just I am going to take 0 comma L or 0 comma phi. Let's note that given function f of x is neither periodic nor even nor odd. First I am going to consider such functions in the interval 0 comma L. If I am taking the period even function, that is minus L comma L, that is different story. If the function is odd in minus L comma L, you know the formulas. Just what I am taking, the important note here, the given function f of x is neither periodic nor even nor odd. In order to obtain the Fourier cosine series for f of x in the interval 0 comma L, we construct the new function g of x, right? We construct the new function g of x such that g of x is same as f of x in 0 comma L. Don't get confused here. G of x is f of x. Whatever function I am taking, this is g of x is same as f of x in the interval 0 comma L. But whatever the g of x we are taking, listen, yes, if you go for the evaluation, it is very easy. Just you are going to understand. I am going to define new function g of x. Right? G of x is same as f of x in 0 comma L. G of x is same as f of x in 0 comma L. 0 comma L, this is a function, right? Next, g of x is even function. Yes, this is the half interval I am considering. If you take the full interval minus L to L, this is the g of x. L, then this is your f of x. Here it is minus L to L. That is, this is the remaining half I am going to consider here. Right? Here is f of g of x. G of x is even function in minus L comma L, and it is a periodic function with period 2L. Right? If you expanding, if you are continuing the f of x, so that function considered to be g of x, which is even in minus L comma L. I am going to consider one case. See this figure, in minus L comma L, the function is even. So that's why even periodic continuation of f of x. So if you see the even f of x in 0 comma L, it is neither even nor odd nor periodic. Neither even nor odd nor periodic. But if we are continuing the f of x to the interval 0 to minus L, then the function becomes periodic, right? And it is a even function. You know that. Yes, such a g of x is known as even periodic continuation function, right? Continuing the function. Actually, we have the function from 0 to L. This is a function. This is the original function. If you are continuing the function to the 0 comma minus L, which is even. If the function is even, so such g of x is called even periodic continuation or extension of f of x. Right? F of x is not a even function, but if you are continuing if you are extending the f of x, we will get the continuation of the f of x, that is the g of x, that is even periodic extension. Okay, the Fourier series now I am going to concentrating on this. Yes, minus L to L. G of x is defined from what? Minus L to L. G of x is f of x. G of x is same as f of x in 0 comma L. But if you consider the interval minus L comma L, g of x is a even function and periodic function with period 2L. Right? If it is a periodic function and even with period 2L, you can expand as a Fourier series, right? Okay. The Fourier series expansion, that means it is a even function, only cosine terms are there. The Fourier cosine series of f of x or g of x, g of x, we can write the Fourier series, Fourier cosine series of g of x in the value in minus L comma L is given by g of x is equals to a naught by 2 plus summation n is equals to 1 to infinity a n cos n pi x divided by L. But here in this case, g of x is same as f of x, no? Right? That means, yes, if it is a even function, the coefficients, right? Now I am trying to write the coefficient a naught is equals to 2 by L integral 0 to L g of x dx. In the interval 0 to L, g of x is same as f of x, right? In the interval 0 to L, g of x is same as f of x. So 2 by L integral 0 to L f of x dx. Let's see the logic. We see the logic. In the interval 0 comma L, f of x is same as g of x. I am writing the same. This is the expansion of g of x, where g of x is an even function and periodic function in minus L comma L. If you are finding if you are concentrating on the finding the coefficients, Fourier coefficients a naught a n. A naught formula, you know that 2 by L integral 0 to L when the function is even. 0 to L g of x dx. In 0 to L, g of x is same as f of x. So 2 by L integral 0 to L f of x dx. Okay. A n is equal to 2 by L integral 0 to L g of x into cos n pi x by L dx. L g of x is same as f of x. So L integral 0 to L f of x cos n pi x by L dx. Yes, if you see the formulas for finding a0 and an, it is clear that same formulas we are taking, but the limits are 0 to L. Even the function is non-periodic, neither even nor odd. By continuing the function is extending into periodic function, so you have the coefficients like this. Okay, since by construction of f of x, g of x are equal in 0 comma L, that is the reason I am replacing f of g of x with f of x. The required half-range Fourier series it is only containing cosine terms. The half-range cosine series of f of x, it is given by 1. It is given by this equation number 1 with the help of equation 2 and 3. This is called half-range cosine series. In a similar fashion, listen, here g of x is equal to f of x in 0 comma L, g of x is equal to f of minus x also in 0 comma L. That's why it is an even function. Note here we see the note here. The series expansion of f of x is given by is valid for f of x only in interval 0 comma L, but not the outside of the interval, right? In a similar way, to obtain the half-range Fourier sine series in 0 comma L. Half-range Fourier sine series means if the function is odd, I am going to take g of x is equal to f of x in 0 comma L. See, same. The function is same in the interval 0 comma L, and g of x is an odd function in minus L comma L. Right? If you are extending the interval, right, the continuation of f of x becomes odd function. If the function is odd, right, function with period 2L. This is a given function. G of x is same as f of x in 0 comma L. Here it is f of the odd function means g of minus x is equals to minus g of x. Here it is this is a given function. If you take negative values of 0 to minus L, it becomes minus. The function is completely minus g of x here, as this is a figure of the odd function, odd periodic continuation of f of x. So the new function g of x is called odd periodic continuation of f of x. So the Fourier series expansion, you know that in the interval minus L to L, minus L to L, it is an odd function. Only sine terms are there. There is no cosine terms. There is no a0. So g of x is equals to summation n is equals to 1 to infinity bn sin n pi x divided by L. But where bn is equals to what? 2 by L integral 0 to L g of x sin n pi x divided by L dx. But in the interval 0 comma L, g of x is equals to what? F of x. So if you replace f of x with the g of x with the f of x, this is 2 by L integral 0 to L f of x sin n pi x divided by L dx. Right? Since f of x and g of x are equal in 0 comma L, the required half-range Fourier sine series expansion of f of x in the interval 0 comma L is given by 4, with the bn's are given by this formula. This expansion 4 is valid for f of x only in 0 comma L, and this is called Fourier sine series expansion or half-range. Why we use the term half-range? We don't consider the complete interval minus L comma L. Here we are taking 0 comma L. Listen, this is applicable for minus pi to pi. That is a special case, minus pi to pi, minus L to L. Right? If you take the minus pi to pi, already we did some problems. Or in case of minus L comma L, we taken. If the function is defined for 0 comma pi. Here in that case, what is the Fourier series expansion 0 comma pi? Summation n is equal to 1 to infinity bn sin nx. Okay. This is called range Fourier cosine series. This is called range Fourier sine series. Sometimes question like this: find the half-range cosine series of f of x. Find the half-range sine series of f of x. It is mentioned in the given problem for half-range sine series. Just you take this formula. No need to evaluate a not a. If you want to find the half-range cosine series, just you are going to evaluate a not a. No need to find the bn, right? Okay. So these are the formulas. Simple problem. Obtain the cosine and sine series for the function f of x is equal to x square in 0 comma pi. Listen, if you take the function f of x is equal to x square in minus pi comma pi, what you are going to expect? Clearly, it is a even function. So we have only a0 and an. Right? We don't have any bn in the interval minus pi comma pi. But here interval is 0 comma pi. No? In this case, we are going to evaluate half range sine series and sine series also. Yes, if we are continuing the f of x in pi comma pi, then the function becomes even and odd. That is different story. Now listen. Now, first I am trying to evaluate half range cosine series. Half range cosine series is given by the formula f of x is equals to a naught by 2 plus summation n is equals to 1 to infinity a n cos nx. Is it clear? 0 to pi is there. That is the reason we have cos n. And if you write the cos n pi x divided by L, L is equals to what? Here it is n pi x divided by L. N into pi x divided by pi. Pi get cancelled. We have nx. Okay. Now here a naught is equals to 2 by pi integral 0 to pi x square dx. 2 by pi x square dx is nothing but x cube by 3. Here, if you take the limits from 0 to pi, we have pi cube by 3 minus 0. So we have pi get cancelled. It is 2 pi square by 3 is the a naught. And an is equals to 2 by pi integral 0 to pi x square cos mx dx. 2 by pi. As you go for the Leibniz rule or integration by parts formula for u into v. So 2 by pi x square into sin nx divided by n minus x square is 2x u v1 minus u dash v2 plus u dash v3. That is the formula, you know that. You are aware about that. 2 by x square sin nx by n. Next x square derivative is next. Here positive is the negative. X square derivative is 2x. Sin x nx integration is what? Minus cos nx. Already divided by n is there. Here it is 1 by n by n. It is by m square. 2x derivative here negative is there. Next positive. 2x derivative is 2. Cos nx derivative is sin nx. Already one negative is there. So same negative we get by n square is there. So n cube 0 to pi. Here limits are 0 to pi. Two n sine terms are there. If you are taking 0 and pi, the sine terms vanish. Right? So only we have the cosine terms. Minus into minus plus. Here it is 2 pi cos n pi divided by n square. 2 pi cos n pi divided by n square. So cos n pi is equal to minus 1 over to the power of n. Next, if you go for the upper lower limit, it's minus 2 into 0, cos 0 is 1. Even cos 0 is 1, but 2 into 0 into anything it is 0. Yes, we have only this term. So x square is equal to 5 square by 3, that is a naught, plus 4 into summation n is equal to 1 to infinity minus 1 over to the power of n divided by n square cos nx. Yes, this is valid in 0 comma pi, right? Yes, but the function if you take minus pi comma pi, only this is a Fourier series expansion. This is a Fourier series expansion. We don't go for sine series, right? Half range sine series, right? Okay, that means there is no negative value. There is no possibility for taking the negative value in a given interval, right? If you are taking the negative f of minus x, if minus x is defined, then you take the function f of minus x. Here the function is not defined for for the negative values of x. Okay. Half range sine series f of x is equals to summation n is equals to 1 to infinity bn sin nx. Bn is the formula. 2 by pi integral 0 to pi x square sin nx. Same integration by parts, x square into minus cos nx divided by n minus 2x into, here it is sin is minus cos is sin, but already the same minus will get here. Sin nx divided by n square, 2 into cos nx divided by n cube. This is vanishes directly. Next here it is 0 is there. Right, it is pi square. First, if you go for the upper limit, pi square or minus pi square, cos n pi is minus 1. If you go for the lower limit, 0 square, it is nothing but 0. 0 into anything is 0. This is already vanishes. Next, if you go for the upper limit, 2 into cos n pi, that is 2 into cos n pi is minus 1 to the power of n divided by n cube. Next, 2 into cos 0 is 1, 2 divided by n cube. So you have this is bn, and substituting this bn, this is x square is equal to, this is the series given by equation number 4. This is the half range sine series. Is it clear? For the half range, the difference between the Fourier series for the function for a periodic function in the interval minus pi comma pi, and Fourier series expansion 0 comma pi. In case of 0 comma pi, don't expect any negative value of x. Yes, if you don't expect any negative value of x, so yes, we don't. Here, if the function given as it is function, we have taken as it is function f of x is equal to x square in minus pi comma pi. This is enough. This is a Fourier series expansion. But whereas in 0 comma pi, we have separately we have evaluated half range sine series and cosine series. Right? This is it clear? It is very simple, but evaluating the integral, again I am telling, evaluating the integral is very important. Also there. And find the sum of the series 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square, so on. See, this is the four afferent cosine series. This is afferent sine series. If you see, you don't get this sum, right? See this one, minus 1 whole to the power of n divided by n square. That is alternatively positive, negativity we have. That means here it is 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square we have. So, I'm going to concentrating on this. So if I'm taking n is equals x is equals to 0, cos 0 is 1. That means we have minus 1 over to the power of n divided by n square we have in the summation. Right? From 2, this is a Fourier half-range Fourier cosine series. So x is equals to 0. We have this. X 0 square is 0, pi square by 3 plus 4 into summation minus 1 over to the power of n divided by n square cos 0 is 1. Okay, here it is first, if I am taking n is equal to 1, minus 1 over to the power of 1 divided by 1 square. Minus 1 over to the power of 1 is nothing but negative. Negative, positive, negative, positive, negative, positive we have. So, I am going to common negative. No? You take out this side and you are going to common negative. Right? You have this. You take out this term to the left side. This is the sum. Next. Find the half-range sine series. Sine series. Similarly, we will get the half-range cosine series also. This the problem is for half-range sine series. For f of x is equal to x into pi minus x, and reduce that in 0 comma pi, and reduce that pi square by 32 is equal to 1 by 1 cube minus 1 by 3 cube plus 1 by 5 cube minus 1 by 7 cube. Half-range sine series expansion is given by f of x is equals to summation n is equals to 1 to infinity bn cos nx. Yes, what is the reason why I am taking cos and sin nx, cos nx? The interval is very important. 0 to pi is there, just you take it. If 0 to L is there, then n pi x divided by L. The formula also different, right? So Bn is equals to, you know that by the formula 2 by pi integral 0 to pi f of x sin nx dx, pi x minus x squared sin nx. So you go for integration by parts, pi x minus x squared into the u into b1. Sin nx derivative integration is minus cos nx divided by n minus the derivative of pi x minus x squared is pi minus 2x, and the integration of cos nx is sin nx minus as it is n by n, that is n square. Positive, negative, next positive. So minus 2. Yes, pi minus 2x derivative with respect to x is minus 2 sin nx. Sin nx integration is minus cos nx by n. The already minus is there, that minus into minus plus. See, one sine term is there. So if you take the limits from 0 to pi, this is vanishes. So this is vanished. Only we have this terms if you take the limits and right, first you go for upper limit. Pi into pi, pi square minus pi square 0. You think it is 0, no problem. If you go for the lower limit, pi into 0 minus 0, 0. The first one is 0, second one 0, only third one we have. Plus into minus minus, minus 2 by n cube. Cos n pi. Cos n pi is nothing but minus 1 over to the power of n. Minus cos 0. Cos 0 is 1. This is the bn 4 by pi n cube into 1 minus 1 over to the power of x into pi minus x is equals to summation n is equals to 1 to infinity bn sin nx, summation n is equals to 1 to infinity 4 divided by pi n cube 1 minus 1 over to the power of n into sin nx. Right? You take out the term, this 4 by 4 it is only see this. If you are taking n is odd, minus 1 over to the power of n is what? Minus 1. So what we have? 2 we get 2 into sin nx. N is odd. N is even 1 minus 1 is 0. Only odd terms we have. That's why 2, if you are concentrating on the odd terms, so we'll get 2. The 2 into 4 it is 8. 8 divided by pi. So only odd terms we have. Even terms is 0. So sin of, that is the reason I am replacing n with n minus 2, n minus 1. Whatever n you are taking, only odd terms we get. Sin of 2n minus 1 into x divided by 2n minus 1 whole cube. Right, to get the required reaction, I am going to replace x with pi by 2. Pi by 2 into pi minus pi by 2, k divided by pi. Summation n is equal to 1 to infinity sin of 2n minus 1 into pi by 2 divided by 2n minus 1 whole cube. Yes, odd multiple of pi by 2. Sin pi by 2 is 0. Sin 3 pi by 2 is 0. Any odd multiple of pi by 2, even multiple of pi by 2 is sin pi. That is different story. Here it is sin pi also 0. Odd multiple of pi by 2 it is alternatively 1 minus 1. 1 minus 1 we get, right? Minus 1 whole to the power of n actually. So we have sin pi by 2 sin 2n minus 1 into pi by 2, that is minus 1 whole to the power of n, and you take out the terms. Here it is pi by 2, here it is replace it. It is not pi square by 32, pi cube by 32. It is pi by 2 into pi by 2, pi square by 4, and here coming to denominator, and this pi coming to numerator, pi cube by 32. As if you take the terms, first one positive, 1 by 1 cube, next n is equals to 2. It is 2 minus 1 sin 3 pi by 2 is negative, right? That is minus 1 by 1 cube, minus 1, plus sin 4 pi by 2 is sin 2 into 3, 6, minus 1, 5 pi by 2. It is positive, right? Like that you will get the terms. This is uh, the value of 1 by 1 cube minus 1 by 3 cube plus 1 by 5 cube minus 1 by 7 cube, so on. In this problem, you can find the half-range sine series, cosine series also. Next, expand f of x is equal to x square minus 2 as a Fourier series in the interval minus 2 comma 2, right? Or find the Fourier series expansion of f of x in minus 2 comma 2. This is the problem not comes under the half-range sine series, half-range cosine series. Is it clear? This is even the minus 2 comma 2 is it is a periodic function with the period 2. Is it clear? Okay. Now since f of x is equal to x square minus 2, but even though it is not comes under the half-range sine cosine series, but the problem the function is even function, only cosine terms are there. Yes, it is, we don't find the b here. Since f of x is equal to x square minus 2 is an even function, then f of x plus expansion is like this. Plus summation is equal to 1 to infinity an cos n pi x divided by l, where l is equals to 2, which is a naught. This is the value. This is an. A naught is equal to 2 by l, that is 0 to l f of x dx, 2 by 2 integral 0 to x square minus 2 dx, x cube by 3 minus 2x. If you take the limits from 0 to, you will get minus 4 by 3. That an is equals to 2 by l, 2 by 2 integral 0 to 2 x square minus 2 cos n by x divided by 2. See, the same, the finding the evaluation of integral u into v dx is same. Right, in this case, u into u is x square minus 2. The integration of cos is sin n pi x divided by 2. See the quotient. In the previous one we have n, we have divided by n square divided by n cube written. Here it is n pi by 2 is the quotient divided by n pi by 2. Yes, divided by n pi by 2 is nothing but 2 by n pi into 2 by a by b by c. B by c is a fraction, then 2 by n pi. Is it clear? Okay, next. The derivative of x square minus 2 is what? 2x. 2x into the integration of sin is what? Minus cos n pi x divided by 2 by n pi by 2. Already, that is n pi by 2 is nothing but 2 by n pi. Already one 2 by n pi is there. 4 by n square pi square. This 2x derivative is what? 2. Sin cosine derivative is sin. Already negative is there. 2 into minus sin n pi by x divided by 2 divided by n pi by 2, that is 2 by n pi into 4 by n square pi square, that is 4 into 2 divided by n cube pi cube. This is the way of evaluating the integral u into v dx. Right, you take the limits and substituting, you will get like this. Okay. In the same way, is it clear? This is an, this is the expansion. So you are trying to solve these problems now. Yes, f of x is equal to x minus x square in minus 1 comma 1. X minus x square, is it even or odd? It is neither even nor odd. You are going to find a naught, a n, b. F of x is equal to x plus b in 0 comma 1. Half range sine series you are going to evaluate. Half range sine series. Find the half range cosine and sine series for the function f of x is equal to x in 0 comma 2. Right, it is the identity function. F of x is equals to 2x minus x square in 0 comma 2 half range cosine series. This is the problem on half range cosine series. Find the Fourier series expansion of f of x in the indicated interval. Okay, here in this case you are going to take this is the function. This problem comes under the previous class. F of t is equal to 0 for minus l less than t less than 0. E sin omega t if 0 less than t less than, yeah. we will get a naught is equals to 2e divided by pi, an is equals to minus 2e divided by n square minus 1 into pi, or here it is valid for n is equals to 246. What is the reason here n is equals to 246? If you are taking n is equals to 1, the function is not defined. We did one problem, right? That is the reason it is valid. Here is b1 is equal to e by 2. You are going to find bn is 0 for every n. For n is equal to 2, 4, 6, so on. Yes, b1 is equal to e by 2. Right? Okay, next. I expand f of x is equal to e to the power of x in minus l comma l. General. F of x is equals to x in defined in 0 comma 1, 0, 1 less than x less than 2. There's a problem from 1, 2, 3, 4. These from the previous class. It is not related to the half range sine and cosine series. Try to solve these problems. This is about the Fourier series. Very simple chapter. In this unit, we have one more Fourier integral theorem. Next class, we will discuss Fourier integral theorem, the problems on the Fourier integral theorem, the existence of the Fourier integral theorem. Okay. In the Fourier series, what we have discussed here, expanding the f of x as a Fourier series in minus pi comma pi. In case of even function and odd function also, expanding f of x as a Fourier series in minus l comma l in case of even and odd, expanding f of x as a half range sine series, half range cosine series in 0 comma pi and 0 comma l, right? This is about the Fourier series. Try to take the notes. That's note taking also very important.